मैग इट्स मैग्नेटिक इफेक्ट ऑफ करंट। ध्यान से पढ़िए असाइनमेंट में क्या लिखा हुआ है। एवरीथिंग इज रिटन क्लियरली। Everything is written clearly. Okay, today's topic is magnetism. After finishing magnetic effect of current, we are moving towards this chapter, magnetism. All of you might have seen the bar magnet, properties of bar magnet. Yeah, bar magnet. So, bar magnet is nothing but a rectangular magnet. It is called a bar magnet. Okay. Now, this magnet has a geometrical length, and actually, this length is called geometrical length. This particular part, I may call it geometrical, geometrical length, geometrical length. Okay, and every magnet has two poles. All of you know it. Two poles. Now, what are poles? How will you define the poles? That is a region near the end of a end points of a magnet where the attraction power of the magnet is concentrated. I mean, the attraction power of the magnet is higher at the two ends. So that region is called poles. This region is called poles. Yeah. Uh, So poles are the region near the end where the strength of the magnet is supposed to be concentrated. The strength of the magnet is supposed to be concentrated. Actually, maximum power is concentrated here. If you move towards the middle point, then power of the magnet decreases. Okay? So this is called north and this is called south. Actually, north and south poles are nothing. But if you suspend a magnet, like a freely suspended magnet. Now, this freely suspended magnet has one pole towards geographical north. Okay, geographical north, the pole of the magnet which is towards geographical north is the north pole of this magnet, and which is the other one which is towards geographical south is the south pole of the magnet. So these are north and south pole. That is, north seeking pole is north pole of the magnet, and south seeking pole, I mean geographical south seeking pole, is called south pole of the magnet. Now we are defining magnetic pole strength. Pole strength is the strength of the pole and denoted by a symbol M. This is plus M, this is minus M. And if you take the center to center distance, I mean center of north pole to center of south pole, then this distance is called magnetic length. This is called magnetic length. Should I write like this? This is magnetic length. So there lies some difference between geometrical length and magnetic length. So magnetic length is, I mean distance between north and south pole of a magnet. I mean center of north pole to the center of south pole. This is called magnetic length. And geometrical length is, that is from geometry end to end. This is called geometrical length. So now geometrical length is always greater than magnetic length. If you take the ratio of magnetic length by geometrical length, that ratio is nearly 0.8 or 0.7. 0.8 or 0.7. So less than 1. Obviously, because magnetic length is smaller than geometrical length. So once you see this property, but if you divide a magnet, now both the poles have equal pole strength. North and south, every magnet has two poles, north and south, and both the poles have same equal strength. So this strength is called plus M, and this strength is called minus M. This is sometimes known as magnetic charge, plus M, minus M, north, south poles. So now, if you divide a magnet, one thing I want to discuss with you, magnetic dipole moment, similar to that of electrical dipole moment. Magnetic dipole moment. So magnetic dipole moment is what? A small m, and if the magnetic length is 2L, we represent it by a symbol 2L. I mean separation between north and south poles, nothing but magnetic length. So pole strength into 2L, this gives the magnetic dipole moment represented by capital M, M into 2L. And magnetic dipole moment is a vector quantity. It is a vector quantity. And if it is a vector, the question arises what will be its direction. Direction of magnetic dipole moment is from south to north pole. It is a vector quantity and is directed from south to north. Directed from S pole, south pole to north pole of the magnet. Now once you know the magnetic dipole moment, which is a vector quantity, now if you divide the magnet into two equal parts, see, now we are going to divide the magnet, bar magnet, into two parts like this. Means we are cutting it perpendicular to its length. So that it will be divided into two equal parts. So then this first part has magnetic dipole moment. So here the pole strength will not change. Pole strength will remain same. And if it is north pole, this is south, earlier this is north, south, then here north pole will develop and here south pole will develop. If you bring them in contact, again they will become the one full magnet. So south pole, north pole, south pole, north pole. Now it is divided into two magnets, and these magnets, if you see, compare this magnetic dipole moment of this smaller part with this bigger part. So bigger part has magnetic dipole moment small m into 2L. So small m plus m minus m is the pole strength, and this is 2L. It's magnetic length. So when you divide it, the magnetic length will get reduced. This magnet has magnetic length L and this magnet has magnetic length L. But the pole strength will not change. Pole strength will remain same. Here it is plus M, this is minus M, plus M, this is minus M. For south pole it is minus M, for north pole it is plus M. So now the new dipole moment, M dash, of one of the part, suppose we are talking of this part, then M dash will be small m into, now instead of 2L we are writing L only, because the magnetic length becomes half. So earlier it was 2L, now it is L. So M into L, from here it is M by 2. So should I write M by 2? So magnetic dipole moment of one piece, it becomes half of the original magnet if you divide it like this. But if you divide the magnet in this way, that is parallel to its length. So now we are cutting this magnet, this section. Then the first part has dipole moment, and this is one of the part, and this is another part. Okay. Now this was north, south. Now here it is north only, south, south. The thing is now the two parts will not attract each other. Rather, this is south, so they will repel. Now you cannot join it. because south pole will repel this south pole, north pole will repel this north pole. But the pole strength, that is M, becomes half because you are dividing this region into two equal halves. So then this pole strength becomes plus M by 2. This is minus M by 2. Again, this is plus M by 2. And this is minus M by 2. Okay. But magnetic length will remain same. Magnetic length will remain 2L only. Now, earlier, the magnetic dipole moment, M is equal to small m into 2L. Now, magnetic dipole moment of the one part, M dash. Now, pole strength is M by 2 into magnetic length is 2L only. So, again it is M into L. So, M into L is how much? Yeah, it is again M by 2. Half of this. Half of this. Okay. So, now this part, Sneha, can you take the snapshot of this portion? Because my mobile is put on recording mode. So if I take the snapshot, that recording mode may be disturbed. So you just take the snapshot. Okay. Okay. You take the snapshot of this portion. So this way you can understand how the magnetic dipole moment will change. And at the same time, a magnetic dipole moment is a vector quantity. Now, should I rub this board? Yeah, this board all of you have written. Now we are talking about that derivation. Actually, magnetic dipole moment is a vector quantity. So, magnetic dipole moment, dipole moment is a vector quantity. Vector quantity. So remember, the addition follow the vector addition, law of vector addition. So if you have two magnets, there's one, the other is like this, and they have equal magnetic dipole moment. Magnetic dipole moment of this one and this one, in magnitude they are same. So this is suppose north pole, or I am writing here south, here is north, here is south, here is north. But the thing is, you can't put it like this. So you have to bind these two ends with the help of a thread. Then only it will be remain in this position. Now magnetic dipole moment of first one is suppose M, and second one, actually they are differing in direction, so magnetic dipole moment in magnitude they are same. So I am writing M1 vector, and here it is M2 vector. With the condition that M1 is equal to in magnitude equal to M2, let it be M. M1 equal to M2 is equal to M. Okay. The angle between their axis, magnetic axis, this is called magnetic axis. The line joining the north and south poles is called magnetic axis. Similarly, there is a geometric axis. So, geometrical axis is maybe sometimes differ with the magnetic axis, because geometric axis is the line which is, just divide the magnet into two equal parts along the length. But magnetic axis may be different from that one. So they may, in most of the cases, they coincide, but in some cases they may not coincide. So M1 equal to M2, and this angle is 60 degree. So now what is the equivalent magnetic dipole moment? So calculate the equivalent net dipole moment. Net dipole moment of the system. So how will you find this? It is very easy to find because it is a vector quantity, and if it is net is m dash, then m dash is vector sum. That is m1 square plus m2 square plus 2m1 m2 cos of 60 degree. So p square plus q square plus 2pq cos theta. So m1 is m square plus 2m square into cos 60 degrees half. Yeah. So this is under root 3m square. So this is root 3m. Is the new net magnetic dipole moment. But if I reverse it, just reverse this magnet, then you need not to tie these two poles, because then this is south, this is north, they will attract each other. So we are reversing one of the magnet. If I reverse this one, then do you think that your magnetic dipole moment will be still root 3m? Yeah, root 3m. It, it will change. It will be more or less. Then, then if you put the magnet like this, now the two magnets are placed. Okay. Now this is north, this is south. Okay, this is north, this is south. And this angle is 60 degree. Okay, these are magnetic axis. Magnetic axis. And this angle is 60 degree. 60 degree. Now dipole moment of first one is along this way, m1. And the second one is south to north. This is m2. Then you have to consider this angle. That is, one of the vector is m1, another vector is m2. So you have to think about this angle. So this angle is how much? 120 degree. Then net dipole moment, if it is m, then m is again m dash, then under root m1 square plus m2 square plus 2m1 m2 into cos how much? 120 degree. So this is under root m square plus 2m square cos 120, minus half. Minus half. So this 2 will cancel out. This minus m square plus m square cancel out. So this is m square only. That is m. So m dash is equal to m only. If the magnets are placed as shown in the figure. Okay. So the net dipole moment, and the direction of net dipole moment is given by completing a parallelogram. So just complete a parallelogram. This diagonal will give the net dipole moment, m dash. Here also this is given by completing a parallelogram. Just complete a parallelogram, and then resultant m dash will be given by this way. Yeah. So this is the direction of m dash. Obviously, the two dipole moments are equal. So this angle will be 30 degree. It's angle bisector. Here also, this angle will be 60 degree. You can consider this one as 60 or this one as 60. So this is 60 degree. Dipole moment, I mean net dipole moment, resultant dipole moment. makes an angle of 60 degree with M2 or M1. Here net dipole moment is making angle 30 degree with M1 or M2 because it will certainly lie along the angle bisector. So angle is 60 degrees, so it will be divided by 230 degree. Clear? Am I clear to you? Yes or no? Yes, sir. Yes, sir. So then moving towards, have you taken the snapshot? Yeah. So now we are moving the another magnetic field due to a bar magnet. Okay, have you taken? Yes. So magnetic field of a bar magnet, similar to that of electric field at a point axial line due to a dipole at a point on the axial line and perpendicular bisector. In the same way, you can find the magnetic field of a bar magnet. So write down magnetic field at a point on the axial line of a magnetic dipole. Magnetic dipole. Okay, this is our heading. Magnetic field at a point on the axial line, and similarly on equatorial line we can derive. So here is a magnet. If you recall your memory, we have already done in electrostatic chapter, that is electric field at a point on the axial line of a dipole. In a similar way, you can find it. So this is suppose north pole. So north is plus M, the pole strength, and this is south pole. So south is minus M. Now this is magnetic axis, axial line. And consider a point P, say at a distance R from the center, R or X, whatever you can think, R. At a distance, at a distance R from the center of the magnetic dipole. So here is center. And this whole distance is 2L, you know. So this half part will be L and this half part will be L. Now can you tell me what is the distance of P point from this north pole? Yeah, this will be R minus L. And similarly, what is the distance of P point from the center of the south pole? Yeah, this will be R plus L. Okay. In electrostatics, we are talking about center of charge. And here we are talking about center of magnetic poles, like similar to center of mass, center of north poles, center of south poles, because north and south poles are not a point, it's a region. So there must be a center. I mean center of mass, like center of charge, like center of poles. So you have to take the distance between the center of north poles, center of south poles, which is different from the geometrical length. Geometrical length is end to end. So this is R plus L. Now magnetic field. Start writing. Magnetic field at P due to north pole of magnet, I mean dipole. So if it is B1, then B1 is mu naught by 4 pi, okay, plus a unit pole here, I mean a pole which has strength equal to unity, and then what is the force exerted by this pole, north pole, on unit pole? So that unit positive pole. So this will have M similar to that of electrostatics. 1 by 4 pi epsilon naught q by r square. So instead of q, you will take this one and divided by this distance square. So r minus L whole square. And the direction will be, since it is positive, so it is away. So from north pole, away from the north pole. I mean, this is along px. Name it as px. It is along px. Okay. Now magnetic field, similarly, magnetic field at P, point P, due to south pole of the magnet, Okay. So then south pole, if it is B2, then B2 is mu naught by 4 pi m. Don't take plus minus m. You are writing magnitude only. So here also we have taken m. For south pole we have taken m, pole strength, divided by this distance square. This is r plus L whole square. Direction will be, yeah, assume here a positive charge, I mean positive magnetic poles, then positive, negative attraction. So it is along P2S. So along PS, P2S means this side it is B1, here it is B1, and this side it is B2. Now which one is greater out of B1 and B2? Obviously B1 will be greater. Since mod of B1 is greater than B2, so net field at P will be towards B1. Therefore, net magnetic field at P due to dipole, magnetic dipole. So then magnetic field is equal to B1 minus B2, two vectors in opposite direction, this side. Similar to, you have already studied in electrostatics, minus Q plus Q. Instead of minus Q plus Q, here it is plus M minus M, magnetic charge. And in electrostatics, it was treated as electrical charge. So B1 minus B2. So just subtract them. Your answer will be mu naught by 4 pi, then M common, and then 1 by R minus L square minus 1 by R plus L whole square. Okay. So this is mu naught by 4 pi. Only the constant in electrostatics, it was 1 by 4 pi epsilon naught. Now your constant is mu naught by 4 pi. The value of mu naught by 4 pi is 10 raised to minus 7 into M. This M stands for pole strength, that is magnetic charge. And then take the LCM, R plus L square minus R minus L square divided by, this is A plus B, A minus B square. Okay, so R square minus L square whole square. No problem? Okay. Now this is net field. Yeah. Yeah. No. So I'm writing the remaining part here. I have some space, so we can utilize. Okay, so putting a star mark here, just to understand the continuity, star mark. Now, net field B equals to, it's mu naught by 4 pi M, and then A plus B whole square minus A minus B whole square. It's nothing but 4AB, 4AB divided by, denominator is R square minus L square whole square. Am I right? Yeah? Do you have any problem? No, 4RL by R square minus L square whole square. Okay. Should I write mu naught by 4 pi? Okay. Then this is 2ml into 2r. What's problem with you? No? It's very simple. If you multiply all these factors, you will have this one. Now, why I have written like this? Because 2ml is nothing but capital M, magnetic dipole moment. Remember, magnetic dipole moment is a small m into 2L. So, small m into 2L magnetic length, this gives you magnetic dipole moment. Now, you are writing mu naught by 4 pi, then capital M, 2, this capital M, this R divided by R square minus L square whole square. Okay? This is B. Now, who can tell me the direction of B? Yeah? Direction along Px. Along greater of the two vector. So, B1 and B2. Yeah. This is along B or what you say along Px? Along Px. In figure, it is along Px. Okay? Now, I have to rub this board. Uh, yeah. Because denominator of this one. If you just compare the denominator, you will understand why B1 same. Okay. You just take the snapshot. Done, done. Huh. This is still your feelings. Any problem? Any problem? Huh. Uh, Charge, similar thing is here, plus M, minus M, these are magnetic charge. In electrostatic, that was electrical charge. So instead of plus Q minus Q, you are taking plus M minus M. Then magnetic field due to plus M at P point is, in electrostatics, this was 1 by 4 pi epsilon naught Q by this distance square. Now in magnetism it is plus M, don't write plus minus because you are writing magnitude. So M by R minus L, this distance is square, this distance is square. Similar to that of electrostatics. Okay? It's a uh, then I can rub this portion. Uh, moving, yeah. So this part is for short dipole. Okay. Writing for small dipole, short dipole. So for a short dipole, in case of short dipole. So in case of short dipole, this R is much, or you may say L is very less than. So when R is much greater than, L, then your expression becomes B equals to mu naught by 4 pi 2mr divided by R square minus L square. Now ignore L square. And the denominator is R square whole square. So this is R4. So left with mu naught by 4 pi 2mr not R, now 2m bar cube. You just recall, in case of electrostatic, this was 1 by 4 pi epsilon naught 2p by r cube. 2p. That p stands for electric dipole moment. But here m stands for magnetic dipole moment. So only the changes lies in constant, and instead of P we are writing M. P is Q into 2L, here M is a small m into 2L. That much difference. So if you have done it in electrostatics, you can do the same thing in for magnetism also. Not tough. Very easy. Okay. So similarly, we are finding the magnetic field at a point on the equatorial line. Okay. So now we are having this part also. Magnetic field at a point. Magnetic field at a point on the equatorial line of a magnetic dipole. Magnetic dipole. Now, considering the equatorial line. Equatorial line is nothing but perpendicular bisector. So we are considering here a magnet, north, south pole. This distance is 2L, so the half will be L. This is 2L. So that half will be L and that half will be L. And this is a perpendicular bisector, equatorial line. Now we consider a point this is plus M, this is minus M, pole strength. Now consider a point P here. This distance is R, this is center O. Now, how will you find this distance? Yeah, how will you find this distance? Yeah, under root R square plus L square. In a similar way, you can find this distance. It will be same, because if this angle is theta, this will be also theta, because these two sides are equal. So this is also equal to, now I am writing here that portion NP is equal to SP is equal to under root R square plus L square. Okay. So if the two sides are equal, then angles opposite to the opposite sides should also be equal. So these two angles should also equal. Now magnetic field of this plus M at point P, obviously it will be away from point P. Remember electrostatics, for plus Q charge, electric field is away from the charge. Similarly for plus M pole strength, it will be away from the point P, that is along this direction. Consider it as B1. Okay. Now the south pole will attract this unit positive magnetic poles, unit north poles. So then a magnetic field due to south pole is towards the south pole because it is negative. So this is B2. B2. If I ask you what is the magnitude of B1 and B2, your answer will be, so B1 actually it is equal to B2 and is equal to mu naught by 4 pi M by under root R square plus L square whole square. In magnitude they are same, B1, B2, because distance same. Pole strength plus M minus M, they differ in sign only, but strength wise they are same, plus M minus M. Every magnet has two poles and the poles are of equal strength. And if you divide the magnet, howsoever small may be the part, that itself will be a magnet. So magnetic poles cannot exist in isolation form. You cannot get a separate north pole. You cannot get a separate south pole. But in case of electrostatics, you may have the positive charge, separate positive charge, separate negative charge. But magnetic poles always exist in pairs. No one can think about the scenario where magnetic poles, you have only north, you have only south. No, meaningless. So if you divide the magnet, keep on dividing, however small the part may be, that small part, tiny parts, it's itself a magnet. I will tell you later on the view magnetism, that is reason of magnetism from the atomic level. There we will understand. So if you divide, keep on dividing, the tiniest part will also be a magnet. Okay. So then B1 is equal to B2 is equal to mu naught by 4 pi small m by under root itna, means square root will be abolished, and this is mu naught by 4 pi m by under root will be abolished. This much only. Now if I ask you, the vectors B1 and B2 are equal and the angle between them, this angle. So these two are theta theta, so this whole angle will be 2 theta. Exterior angle, sum of opposite interior angles. And then complete a parallelogram, and the diagonal of parallelogram will represent the resultant of two fields V1 and V2. And this is the net field. So then B equals to net field. Net field at B. So then B is equal to under root, say B1 square plus B2 square plus 2B1 B2, and then cosine of angle between B1 and B2. So this is B1, this is B2. So what is the angle? Angle between them is, yeah, tell me. That angle is 2 theta. So angle between two vectors B1 and B2 is 2 theta. Now at the same time B1 B2 are same. So should I write? This is B1 square plus B1 square plus 2B1 into B1. That is 2B1 square into cos 2 theta. This is 2B1 square plus 2B1 square. Take it common. So under root 2B1 square and 1 plus cos 2 theta. Do you have any problem? No? Yeah, children, any problem? It's the square root of 2B1 square. Then 1 plus cos 2 theta, 2 cos square theta. 1 plus cos 2 theta is 2 cos square theta. It's a simple formula in trigonometry. Now this 2, just take it, square root, take out from the square root. That is 2. B1 square is B. Cos square theta is cos theta. This is net field. Now put the value to B1. This is your B1. So mu naught by 4 pi m by r square plus L square. And then tell me what is cos theta. Cos theta from this right angle triangle, this is base by hypotenuse. So this is right angle triangle. So in right angle triangle, cos theta is, I am writing here, cos theta is L by base by hypotenuse. So this is r square plus L square. R square plus L square. So now replace this cos theta. L by under root r square plus L square. See, in numerator it is 2ml. Is nothing but capital M. So now I am going to write mu naught by 4 pi 2ml, capital M, magnetic dipole moment, divided by r square plus L square. See, this is the half power, this is 1 power. So half plus 1, is it 3 by 2? Yeah, this is 3 by 2. So this is for a dipole. But if it is a short dipole, in that case, now the angle of B, angle of this vector is theta only, because B1 and B2 are equal. So resultant will be along the angle bisector. It means this vector is parallel to this vector, anti-parallel you may say. If you compare it with the magnetic dipole moment, direction of magnetic dipole moment, so magnetic dipole moment is from south to north, and net field at P is from this side to this side, from P to something. I can name it PQRS something, PQ R. Don't write S because S you have taken already. So PQRS T. Okay. So this is along the line PR. Along the line PR. Along PR. That is along the angle bisector 2 theta. If you divide 2 theta, this will be theta theta, and this will be along, because this is the resultant of two equal vectors. So resultant of two equal vectors always it lies along the angle bisector. So for a small dipole, now you can take the snapshot, and then I can rub this first part of the board. Yeah. You just take the snapshot. Done. Okay. Now I'm rubbing the upper part. Then for short dipole. For short dipole. So in short dipole again R is much greater than L. So now we are ignoring L square here. So if you ignore L square, then B equals to mu naught by 4 pi M by, and then R square raised to 3 by 2. R square, this 2 will cancel out. So in denominator it is R cube only. This is on equatorial line. Equatorial. But in axial, remember, this was mu naught by 4 pi 2m by R cube. So there exists a relation between magnetic field at a point on the axial line and magnetic field at a point on the equatorial line. So relation between magnetic field at a point on the axial and equatorial line of a dipole. Dipole is magnetic dipole. So B axial means magnetic field at a point on the axial line is 2 times the B equatorial. 2 times. So field on equatorial line is half of the field on axial line. So magnetic field is strong on the axial line, weak in the equatorial line. Okay. Now I am putting one small numerical. You can write it. See the magnetic field at a point on the axial line, if it is B, at some distance R, if it is B,